Let's look at another type of calorimetry problem. Here we have a problem where a salt is dissolving in water. Remember, when I use the word salt, it could be any type of ionic compound. In an ice pack, solid ammonium nitrate dissolves in water. When you break open the little bag on the inside, the ammonium nitrate and water mix, and an endothermic process occurs as the ammonium nitrate dissolves in the water. Heat goes into the ice pack from your body, for example. In this example, we have 3.21 grams of ammonium nitrate dissolving in 50 grams of water, which starts out at 24.9 degrees Celsius. The temperature decreases to 20.3 degrees Celsius. We want to find Q for the dissolution process. We're going to use our Q equals mc delta T equation. This time we're doing it related to the solution. The solution is made up of the salt mixed with the water. It's both things combined together. Rather than doing the equation twice, we just need to do it once, but with everything related to the solution. Q of the solution equals mc delta T of the solution. The mass of the solution is not just the 50 grams of water. It is also the 3.21 grams of ammonium nitrate. We have to add both of those masses together to give us the total mass of the solution, which is 53.21 grams. For the C of the solution, we're going to assume the solution is mostly made of water. So its specific heat should basically be the same as water, which is 4.184 joules per gram Celsius. We have two temperatures, an initial temperature of 24.9 and a final temperature of 20.3. Remember, for delta T, we do final minus initial. We plug our variables into our equation. Our mass of 53.21, our specific heat of 4.184, and our two temperatures, final minus initial, so 20.3 minus 24.9. Because delta T is negative, we calculate a negative value for Q, specifically negative 1024.1 joules. The reaction has the opposite sign of the Q for the solution, so it is a positive 1024 joules. In other words, 1024 joules are going into the reaction and out of the surroundings. That's why the surroundings cool down, but the reaction itself is heating up. Another type of process that we can look at with calorimetry is a neutralization reaction between an acid and a base. In this problem, we have 50 milliliters of 1 molar HCl reacting with 50 milliliters of 1 molar sodium hydroxide. They both start out at a temperature of 22 degrees Celsius. When they get mixed together, the temperature heats up to 28.9 degrees Celsius. We want to find the amount of heat produced by this reaction. Again, we're going to use the equation Q equals mc delta T with everything related to the solution. The mass of the solution, that is, the mixture of the hydrochloric acid and the sodium hydroxide solutions, can be figured out by the volumes of the solutions. Both solutions are mostly made up of water, which has a density of 1 gram per milliliter. So 50 milliliters of hydrochloric acid solution weighs about 50 grams. And 50 milliliters of sodium hydroxide solution weighs about 50 grams. When we add them up, we get a total of 100 grams of solution. For C, the specific heat of the solution, we'll use the C of water, which is 4.184, since the solutions are mostly made of water. The final temperature of the solution is 28.9, and the initial temperature of the solution is 22. And again, we're doing final minus initial. Q for the solution is 100 times 4.184, and then we multiply by 28.9 minus 22. And that gives us 2,887 joules for the solution. Again, the reaction has the opposite sign of the Q of the solution. So it is negative 2,887 joules. Heat goes out of the reaction and into the solution. We could say that 2,887 joules are produced by the reaction. Although the Q for the reaction is negative 2,887 joules, we report the amount produced as a positive number. The signs are mostly there to tell us the direction of the transfer.